Welcome back to another episode of Introductory Organic Chemistry. Today we're going to talk about the Friedel-Crafts reaction, as well as the nucleophilicity parameters of Arenes, and finally we're going to talk about the synthesis of THC using a Friedel-Crafts reaction. And since we didn't have any follow-up from last lecture, let's get right into it. So you can add different electrophiles to arenes. These could be carbon electrophiles, like halogen electrophiles, nitrating agents, sulfonating agents, and in general, you can have two different types of directing groups. You can have ortho-para directing groups, which are typically electron-donating groups, or meta-directing groups, which would be an electron-withdrawing group. Typically, as I just said, electron-donating groups tend to be ortho-para directing, and electron-withdrawing groups tend to be meta-directing. But practically speaking, if you're trying to add in a carbon electrophile to an arene, you're usually only going to get addition to occur if you have an electron-donating group, unless you have a really powerful electrophile. There are exceptions, so like nitration and some halogenations are quite powerful, and they'll go even for deactivated arenes. If you can get an N and an E parameter for these, recall that the sum of them should be greater than -5. And so in the case of an electron-rich arene, such as in the case of this dimethylaniline, you can see that if we draw a resonance structure where there's a positive charge on the nitrogen, we can have a negative charge in the ortho position, or if we move the electrons and push them a little bit more, we can have an electron in the para position. However, if we did this with something like a nitro group on a nitroarene, like nitrobenzene, you could see that we could move this up onto the nitro, putting a negative charge on the oxygen and a positive charge in the ortho position and a positive charge in the para position. And because this is a positive charge, you're not going to add an electrophile there because those two charges are just going to repel each other. So if you can add an electrophile, it's going to add to the meta position. And you can see this rationalized through resonance. If you have a different electron withdrawing group like a CF3 or something like a nitrile, it might not be as easy to draw a resonance structure like this, but it still works in terms of relative electron density. So it can still suck electron density away from those two positions. So some things to consider when you're doing Friedel-Crafts type chemistry is that the N parameters of most arenes are not determined. So if you ever wanted to do research and actually contribute to the physical organic chemistry space, this would actually help out experimentalists and theoreticists quite a bit if you could determine more of the N parameters of different arenes as well as the E parameters of electrophiles. In general, if you have an arene, it will have an N between 11 and -5, which is a massive range. That's 16 orders of magnitude difference. And this isn't like a complete list, though. As I said, there's like a massive lack of arenes in the data set. Additionally, there's no electron deficient arenes, not even like chlorobenzene. So, there's a lot of work that could be easily done in a master's thesis or a PhD thesis if you did a really good job. Likewise, if you're looking at electrophiles, you're going to have a hard time finding E parameters most of the time. And so if you have an electrophile, typically it has an E parameter of 10 to -11, but most of them tend to be somewhat negative. And so if we're looking at electron-rich arenes, if we have electron-donating groups, we can see this is the relative order of reactivity. You can see that I've colored the phenoxide as well as the phenol both red, because these are the same molecule, they're just protonated versus deprotonated. And there's no N parameters for the first four. Even though I've listed an N of 4 for this substituted aniline, this is only based on my anecdotal experience of relative reactivity, knowing what electrophiles will react with nucleophiles which do have an experimental N parameter. And so if you add an electrophile to something like phenoxide, it's very easily going to react, and it's probably going to keep reacting 2 or 3 times. So in the case of the nitration of phenol, you typically get 1, 2, 3, 1, 2, 4, 1, 2, 1, 4, 2, 4, 6 trinitrophenol. There we go. So in the ortho, the para, and the other ortho position, because nitric acid is so reactive that it'll just keep adding. Now, in the case of aniline, you can typically add in electrophiles more than once. The other consideration, though, is this nitrogen is a nucleophile as well. So we don't necessarily react at benzene just because benzene can react. It's also possible that the aniline nitrogen could react. Phenol is still quite reactive on its own. Then as we get down to like a nitrogen with 2 R groups, it's fairly reactive. If we have like 2 alkoxy groups, both are ortho-para directors. So this position is the most reactive because it's para and ortho. Practically speaking, most of the time, if you add in an electrophile, it's going to go para because of steric reasons. Now, there are exceptions, but most of the time, if the para position's open, the electrophile is going to go to the para position, especially for aniline derivatives as well as anisole derivatives. Okay, if we don't have an alkoxy group and we just have like an alkyl group, we can see that this is still 3 orders difference in magnitude in terms of reactivity. So this is quite a poor nucleophile, and once we get to benzene, it's even worse. Finally, if we have a weak electron withdrawing group like a chlorine, bromine, iodine, or fluorine, this is actually still a weak ortho-para director, although it doesn't help accelerate these reactions, other than by concentrating some of the electron density in the ortho and para positions. Now, if we're looking at heterocycles, we can have something like thiophene, which is a pretty crappy nucleophile. It's got an N of -1. However, if we switch the sulfur out to an oxygen, we get an N of 1.3. If we add in a directing group on the thiophene, we can see that this position becomes suddenly a lot more nucleophilic by about 2.4 orders of magnitude. So quite drastically more reactive. Additionally, if we add a good electron donating group adjacent to this position, we can see it goes up even more to 3.1. Additionally, you can see furan compared to methylfuran. Methylfuran also gains 2.3 orders of magnitude reactivity. Pyrrole on its own is already quite reactive. If we add a methyl group, though, it still goes up by 1.5 orders of magnitude. Indole and indoles in general are really good nucleophiles. If you add a substituent onto this benzene ring, it can affect the N parameter a little bit, but it doesn't change by at most 2 or 2.5 orders of magnitude. Finally, here we have this azolene, which is an interesting 5,7 fused bicyclic compound, and electrophiles will add in really well to this position. Now, if you're curious about electron withdrawing groups, while there's no N parameters for these determined, there still is known the relative order of reactivity. So here we still have our halobenzene from the previous one, slightly deactivated. Then as we go to the right, a carbonyl makes it more electron withdrawing. A trihalomethyl group such as a CF3 or a CCl3 makes it even more electron deficient. A nitrile is even worse. Sulfonyl containing compounds are even worse. Nitro's like extremely deactivated, and of course the most deactivated would be a quaternary ammonium connected to the benzene. So these do not want to react with very many electrophiles. And so while these are not useful in terms of knowing their N parameters, we can infer that if we have one of these electron withdrawing groups present on our molecule, on our benzene ring, it can really deactivate the ring from further substitution unless we have a really potent donating group like a phenol or something. Okay, so if we look at these electrophiles, we can get an idea of how carbocations tend to be in terms of E parameters. So here we have this cumyl carbocation with an E of 5.7. If we have this dibenzyl methane carbocation, this would be 5.5. However, if we have a stabilizing atom like an alkoxy group, this actually decreases the E to about 3. If we have an aldehyde in the presence of a Lewis acid, like boron trichloride, these are massively more reactive than they would otherwise be. If you recall, aldehydes have an E around -10, so this is a massive E parameter difference in the presence of a Lewis acid. If we then look at this dithiocarbocation, this is like still decently reactive. As we get to this tropylium, it's -3.7. This is actually like in conjugation, so the whole thing is usually drawn as a circle with a positive charge in the middle, but I've drawn this so you can clearly see. Here, this is called Vilsmier Haak reagent. This is one of the two forms which is usually used. It's used to make aldehydes, and it has an E of -5.8. And finally, here's this other dithiocarbocation, which has an E of -5.9. So if you're doing a Friedel-Crafts acylation, usually what is used is an acyl chloride. Sometimes you can take a carboxylic acid and in situ prepare it into the acyl chloride using thionyl chloride or oxalyl chloride. And then you put in a Lewis acid, which is typically aluminum trichloride. This aluminum trichloride just helps rip off a Cl- and make a more naked acyl carbocation, which can usually react in the ortho or para positions. Most of the time para substitution is observed, but you'll see cases where certain groups will direct it to the ortho position. The disadvantage of this is Lewis acids like aluminum trichloride are very harsh and they can tear molecules apart and they can cause other chemistry that you don't want to happen. Usually if you're going to do a Friedel-Crafts acylation, you're going to do this early on in the synthesis to avoid those types of complications. I also want to note that once we add these electron withdrawing groups to the ring, it deactivates it from further substitution most of the time, because the Friedel-Crafts acylation reaction really tends to only ever add one unless you have a crazy strong electron donating group. So this deactivating group just prevents further substitution. If you're going to do something like a Vilsmier Haak formylation, because it's a milder reagent, there's no Lewis acids required unless you consider POCl3 a Lewis acid. These can usually be done with decent regioselectivity. Not always though, sometimes you see mixtures of products in the literature. Okay, so let's see if we can predict which benzene ring containing compounds will react with an electrophile like Vilsmier Haak reagent. So here we can see toluene has an N of -4. Vilsmier reagent has an E of -6. We can just do some quick math, add that up to -10. -10 is already much lower than -5. It probably won't react. Now it gets even worse because in this case we can actually look at the slope parameter, which is just like the coefficient for this calculation. And you can see instead of just having like -10, it's -10 times 1.7. So you have a -18, which is like even worse. So this is a terrible reaction. You're never going to get DMF to react with toluene. Okay, and I say DMF because this is derived from DMF. They prepare the Vilsmier salt just in one step. However, if you take a more electron-rich arene or heteroarene like this indole, which has an N of 5.5, this will react quite well. So here you can see that the sum of these is roughly 0. If we want to be more specific, the sum will be minus 0.22, and then after timesing that by the coefficient, it's minus 0.24. So this reaction will work great. It'll probably even happen at room temperature. We get this intermediate here, which can then undergo hydrolysis and undergo keto-enol tautomerism to reform the aromatic indole, and the aldehyde is unmasked through this hydrolysis. Okay, great. So now some examples of Friedel-Crafts acylations. This is a case of an intramolecular Friedel-Crafts. If you can ever do a Friedel-Crafts acylation or even like an alkylation with an aldehyde, and you're going to do an intramolecular process, these reactions work really well. Even if you think that the ring isn't activated enough, because it's intramolecular, it usually will work quite well. And actually, instead of using aluminum trichloride most of the time, if you had a system like this and you just used hexafluoroisopropanol, this would just work on its own. You don't need any external Lewis acid catalyst. The hexafluoroisopropanol won't esterify the acyl chloride very well. It'll just form a hydrogen bond to the carbonyl, make it more electrophilic, and facilitate this cyclization reaction. In this case, they didn't do that. In this next case, we can see an intermolecular reaction where the fluoride acts as a weak para-ortho directing group, and so the para position ends up reacting, and you again get a really high conversion to this ketone product. Now, if we wanted to do an alkylation, there's several different groups we can use. Most of the time, if you have an alkene or an alcohol or a cyclopropane or an epoxide, you're going to be activating those with acids. So the strong H+ can protonate the alkene, it can protonate the alcohol and eliminate water, which will generate a carbocation. Cyclopropanes can be ring opened with a strong acid, and epoxides can be ring opened using a strong acid as well as aldehydes. Now, if you're going to do an alkyl halide, typically you'd use a Lewis acid catalyst like aluminum trichloride, iron tribromide, and those will do some carbocation rearrangements, but because these are such harsh reactions, you're going to get rearrangement reactions, and it's just not ideal for good chemistry. So if you have a tertiary alcohol or tertiary alkyl halide, these are fine. But if you've got like a primary or a secondary, they're usually going to undergo rearrangement reactions. So here's an example of what a typical Friedel-Crafts alkylation will look like. We usually will go para if it's open. Here the carbocation just reacts on the para position, and you'll lose H+ as a byproduct, which I didn't show. Now in this next case, if you were to take an aldehyde, the reason that you don't want to use these are because they can keep reacting. So we form a benzylic alcohol intermediate. This benzylic alcohol is able to get protonated, form a benzylic carbocation, which can then react with another electron-rich arene, forming this di-substituted product, where the R group from the aldehyde is still retained. So it's worth noting that if you're going to try and prepare a benzylic alcohol this way, you'd usually be better off just doing a Grignard reaction. In the next lecture, I'm going to talk about other electrophilic aromatic substitution reactions, such as halogenations, where you could easily prepare this Grignard reagent instead of just directly trying to put in your aldehyde. Okay, so the next thing I'm going to talk about is an example of the Friedel-Crafts alkylation reaction used in the synthesis of delta-9 THC, more commonly known as THC. As yesterday was April 20th, 420, I thought it would be appropriate to do the synthesis. So here we can see that we take this tertiary alcohol in the presence of a strong acid. A carbocation is generated, which it can be attacked by this ortho-directed diol, which is called a resorcinol. When you have two phenols meta to each other, it's called a resorcinol. This specific one is a component of olive oil. Okay, so this is able to be formed through a couple different reactions that we'll talk about in a minute. However, we have the double bond in the wrong location. This is actually delta-8 THC. And so they have to do some subsequent chemistry to convert this alkene to a tertiary chloride and then re-eliminate to get this delta-9 THC, which is green. Okay, if you want to read the original paper where they do this, it's in German, but if you don't speak English, it won't be very easy. So the mechanism of this reaction is first this hydroxy group is protonated by strong acid. This gives off water. This tertiary carbocation is allylic, and so an allylic attack can occur where the alkene is able to migrate to form the more substituted alkene. Additionally, the phenoxide or the phenol that collapses down forms a ketone, which undergoes keto-enol tautomerism to reform the aromatic system. However, we still have to form a bond between this oxygen and this alkene. So this alkene is able to be protonated, forming a tertiary carbocation, which can be attacked by the adjacent phenol. Through the loss of the H on there, which is an H+, we get delta 9-THC. However, because this is under acidic conditions, this acid is able to protonate this alkene, reforming a tertiary carbocation, which could be deprotonated again, and form the more stable delta 8-THC. And so if your goal was to make delta 9-THC, you'd have to do some subsequent chemistry. So this just happens to be the more thermodynamically stable alkene. So what they had to do is they had to protonate it with a strong acid, regenerate the tertiary carbocation, and then use chloride, trap it out as the tertiary chloride here, which is a mixture of diastereomers. Then using this clever approach using tert-pentyl alcohol deprotonates the remaining phenol, and then because this oxygen is perfectly lined up, it can just deprotonate this position, doing a really awesome intramolecular E2 elimination, forming the desired product. And then because this is under basic conditions, you don't get any interconversion. And so here you go, we've prepared delta 9-THC. The most noteworthy thing from all of this that I really wanted to highlight in this lecture is that almost all of this chemistry can be done using hexafluoroisopropanol in place of Lewis acids. And so it's been used to mediate Friedel-Crafts alkylations for the alkylation of electron-rich arenes with alkenes, with epoxides, as well as acylation, both inter- and intramolecular. Additionally, Michael acceptors have been used as alkylating agents with electron-rich arenes, as well as cyclopropanes. And so HFIP, if you're ever trying to do Friedel-Crafts chemistry and you have access to HFIP, it's really worth giving it a shot because it can easily facilitate these reactions. Usually will give you fewer side products and in higher yields. So it's a great solvent and great mediator for these reactions. You might still need a catalytic amount of a strong acid like triflic acid, but using HFIP as a solvent just cleans up these reactions immensely. It's basically a magic solvent, I like to say, because you can do almost anything in HFIP. It's not a very good nucleophile, but it's a great H-bond donor, so it can be a really good catalyst. So with that, I'd like to assign a few different practice problems. First, predict whether or not you think the following reaction would occur without needing any N or E parameters, just based on what we've been talking about so far. In the next problem, using N and E parameters, predict whether or not the following reaction would occur. And so I've given you the N and the E parameters here. In this final problem, I'd like you to show what product or products would form in the following reaction between this phenol with this alkene in the presence of acid. This is actually used to make propofol. And so with that, I hope that this has been a useful lecture on the synthesis of THC, the use of the Friedel-Crafts reaction, as well as re-examining nucleophilicity and electrophilicity parameters. I would appreciate it if you could leave a like or subscribe. If you have any comments or questions, please leave them below. Have a great day. Have a great day. And, yeah, thanks for watching.